I want to introduce the speaker, Mikhail Galkin, from two institutions, AI Institute from Quebec and McGill University. Mikhail is going to speak about the specificity and IT limitations related to vector representation of entities in graphs. And he is also, using this opportunity, I would like to say that he is a person who works both in Russia and the United States. And after his presentation, as it was the case with previous speakers, dear viewers, you have your QR codes. Please ask your questions. The floor is yours, Mikhail, please.
Hello, my name is Mikhail Galkin, and today I'd like to tell you about the life beyond basic conventional machine learning challenges, beyond shallow embeddings of knowledge graphs. And I will also go into Einstein a few other notes. Now, some reasons for large representations. Today, function paradigm is dominating. For this reason, we are training the models first and then fine-tune them to specific jobs. This is same is ongoing in ML, graph ML. And when we begin working with big graphs, normally they begin to be embedded by node accordingly to structure objects. So for medium-size iterations, these meetings take around 200 gigabytes and are quite cumbersome to process. Also, from a practical viewpoint, turning it into production, it becomes quite expensive. Now, let me tell you more about shallow embedding in tables. This is the paradigm where each node is assigned independent vector. So, if we have a certain vocabulary or number of nodes, each node, each entity accordingly is assigned. So, in the graph, we have tensor, shallow embedding tensor, which is the size of the embedding dimensions per number of nodes. These embedding tables are only usable in in training and inference. Now let me tell you more about transductive and inductive versus inductive. Here we perform classification, look for links. The number of nodes doesn't change. All the entities are known during training. Accordingly, inference is supplied with a completely new graph or new entities, new unseen nodes, or entities that had not been yet seen, so we had not pre-trained embeddings. And so transductive setup cannot use shallow embeddings because this approach cannot be used. We don't have any basis, any foundation for this in the nodes. We either need more powerful encoders, more powerful approaches to use them for inductive tasks. A few more words about the non-optimal shallow embedding approaches if we look at the modern benchmarking. For instance, WikiKG, this is part of the Open Graph set, WikiKG 2.5 million node in size. We can see that the best algorithms in the first rankings take up to 500 or a billion nodes, and we see that series vector 340 and Big Bird, which created a revolution in LP. We can do so much more with language models. It uses 300 million and more, and if we take the embedding embedding algorithms that are way over 1 billion parameters in graphs. We do not see these approaches create a disruption in graph making sector. So, is there life beyond shallow embedding? Or do we really need to learn and store the whole shallow embedding matrix and try to fit it into small nodes, into small systems? So does it make sense to store 200 gigabyte? Can we do something more economic without losing efficiency? So the answer is yes. And I'll tell you about 2 pieces of work out this year. One of them is neural Bellman-Ford nets, and second is NodePIS. Let me begin with the first neural Bellman-Ford nets. We're all aware of the classical Norman-Ford algorithms from computer science and algorithms data structure courses. Standard programming for shortest graph. Key iteration is pictured here. States then updating the distance to current nodes. We take the minimum distance from the previous node and the distances from V2, V3, V1, and accordingly standard algorithm in this case does the processing. The authors of the article came up with an interesting way to join these iterations, to scale these iterations to new operators. It generalizes plus to any operator. We can also change operator minimum to any operator. However, these 2 operators have to create a mathematical semi-ring system. This is the point, and if we change these operators with a more generalized, we get the generalized Bellman-Ford curve, and the equation there arises the node equations, scanning, then processing, and the operations run in the same way as Bellman-Ford. However, we can use also not just pluses. And the last trick is parameterizing this generalized data, and at the end we receive aggregate messages, stand message passing, which can integrate the aggregate messages and indicator. You see it at the bottom. So parameterizing these operators, we receive a rational GNN, and accordingly this was the scholar approach to Bellman-Ford regarding neural networks. And the authors state that this generalized presentation of Neuron-Ford, it recovers many standard algorithms if we begin to vary the functions. So accordingly, we can get a personalized page rank if we change the aggregator functions, play around with the indicators. And in every projection, many algorithms are recovered from these types of framework. And the reason we are interested in this approach is that we don't learn no trainable entity embeddings exist. The only trainable entity here, instead of old-fashioned tensor, the E is multiplied by 1, which is a great saving. And on a relationship trained, accordingly, it's inductive out of the box. Since inductive tasks, the predicative links are the same. And accordingly, we can build it into the message passing frameworks, and accordingly use standard message function with any pairwise function, string C, just rotate E, etc. And accordingly, we get a representation of every mode as NLP from different layers. 6 layers, 6 iterations, but we have to run it through the node in this case according to vectors. Table 8, number of parameters in NBFNet. Number of parameters only grows with the number of relations. The numbers here used to take 300 million parameters. Accordingly, since Bellman-Ford is not trainable on embedded entities, these models suffice with 300,000 params, and this reaches much more values than the state-of-the-art shallow algorithm. So we see some significant improvements over the last few years, and standard data sets used with standard data sets becomes one of the top algorithms for 2021. Now back to 2014. Let's come back to Word2Vec. And Word2Vec used to remind us of shallow embedding because every word was assigned own vectors, and accordingly all the words that were not part of the vocabulary were marked as out of vocabulary token, and so accordingly these words were unknown after training, were marked with this out of vocabulary token. Accordingly, it led to huge tables in byte, and pretty soon a new way was developed for word encoding, which is called byte pair encoding or word piece. When we break down the words into frequency tokens, so we can create a fixed size vocabularies and current languages, prepare 30 to 50,000 tokens per language, and we can tokenize any word accordingly. So even the letters, words will always be part of our vocabulary after tokenization. If we try to express this idea through graphs, does tokenization work with graphs? If nodes in a graph are words, can we design a fixed size vocab tokens? We will endeavor to answer this question in our project, which is designed to be somewhere in the middle of language models, using serious encoders and between KG embedding models that uses all of the vocabulary parameters and non-parametric scoring functions, arithmetic and algebraic operations. That the design uses a vocabulary, tokens, and an encoder that recreates representations. So if we compare this against the language models, shallow models use only known words, otherwise OOV. However, if we extrapolate the concept to graphs, all of the graph learning algorithms are shallow models, and we present a different way called subword units, a word piece model. Now, what is the idea for node piece subword units for KGs? Accordingly, we still have vocabulary anchors plus relation types, and it's inductive out of the box. Unseen nodes are tokenized with the same vocab. Accordingly, we have some anchors in our graph. We can triangulate this anchor, any node in our graph, as a sequence using the context surrounding our target node. This model, as I said earlier, is inductive out of the box because we are tokenizing unseen nodes with the same vocabulary in the same graph. Now, base tokens can be selected as anchors. They can be selected through top distribution, top page rank, or random. It all depends on the graph. and different strategies for different graphs may be used. Accordingly, we use a set of anchors, and we're able to tokenize any node. Let's try to tokenize Einstein in this graph. For instance, we have the place of birth, the theoretical physics Nobel Prize, and we are able to tokenize Albert Einstein as 3 nearest anchors and 4 unique outgoing relations predicates in the context. Accordingly, what happens next? With every new node, we see it connected to the graph, and if it has at least one rib, we use GFS, and the search will look for the nearest anchors. Accordingly, we can use the learning model for our anchors and encode the entity's new node. Since all the nodes are known, and also unseen nodes were taught in similar ways, there is no difference between transductive and inductive setup. In this case, set encoder injective may be using any function AVG, MLP, or vanilla transformer in any variation. Your favorite set pooling model, NLP, transformers work equally well, but with different time costs. And what is interesting to note, this can be used on any machine learning tasks. Trajectory, we're able to materialize all the node elements, put them into a GNN, and focus it on any job. Basically, we have tested that actually on 5 different tasks, ranging from classification to prediction, and also in different setups, transductive and inductive. So if we look at the experiments, we will see that the situation level, transductive link prediction graphs are the dependency. We need to learn to find out how many nodes are necessary for every node to effectively code the nodes without losing efficiency. And here we can show that Freebase, for instance, that uses many unique connections, 25 to 50 anchors per graph, is a sufficient volume out of 15 compared to 15,000. This is huge savings, and saturation happens quite quickly, so we can effectively encode nodes 10 to 20 anchors per node. So the length per word becomes from 10 to 15 tokens. And stronger graphs need more anchors, but the number of anchors per node is also saturated by a factor of 20 to 30. And if we look at the visualization of trained entities, we will see that anchors actually identify the community in a way. Color-coded red, we see the anchors, and color-coded blue are the recovered, reconstituted nodes. Accordingly, Freebase and other graphs for every entity, for every community, uses at least one nearest anchor that provides a root representation of this community and uses composition edge features, accordingly providing a certain number of nodes centrally placed, and they slightly change the representation, creating thereby such communities. Now, the good news, we have achieved OGB. We were using OGB WikiKG2. We created a new SOTA, so 2 million graph node. It was very quickly done, and 0.3 was the node piece plus auto SF, so quite a good result. 100 times smaller size, more parameters may be fitted, saturated, and a well-performing model may be developed. Implementation of all of these approaches is described. Articles are out in open access, open GitHub. Also, this is over for my presentation. There is life beyond shallow embedding. So if you're interested, please contact us.